In this video, we're going to discuss how to graph the derivative function if we're given the graph of a function. So we maybe are given the graph of a function, but not its formula. How can we use properties of that function and what we know about the derivative to actually graph the derivative function? Now we're going to need to recall some basic facts about derivatives and tangent lines and so on and so forth. So let's say we have a function that's increasing. Maybe the function looks something like this, maybe the function looks something like that. In both cases, if I draw a tangent line to the curve, the tangent line will always have a positive slope. But the slope of the tangent line is just the derivative. So that means the derivative function is always positive, which means the derivative graph, whatever it looks like, has to live above the horizontal axis. So f is increasing means that f prime is positive. Let's take a look at the flip side of the coin. Let's say a function is decreasing, so maybe the function looks like that, maybe the function looks like that. At each point on either curve, the tangent line slope is always negative, but the slope of the tangent line is the derivative. So the derivative is always negative, which means the derivative graph, whatever it looks like, has to live below the horizontal axis. Now, here's another situation. Let's say we have a curve that maybe it opens up like a parabola at the origin. Maybe it opens down like a downward parabola. So maybe it has a local min at the origin or a local maps. Or maybe the curve comes in like this and is temporarily flat and before it starts going up again. In all three of those situations, if I draw a tangent line at the origin, it's horizontal. Well, a horizontal line has a slope of 0. So if the tangent line has a slope of 0, and if the derivative is the slope of the tangent line, that means regardless of which of those three situations I'm looking at, the derivative has to equal 0 there, or have a horizontal intercept. So again, if the graph of f is flat at a point, the derivative has to have an intercept there. What about corners, sharp edges, things like that? If a function has an undefined slope at an input, for example, a corner or a cusp, then the function derivative is undefined there. So let's take a look at the absolute value function. We know that it has kind of that V shape at the origin. I cannot draw a well-defined tangent line, so that means f prime of 0 does not exist. So if I went on the derivative graph to x equals 0, there's not going to be anything on the graph there. The same thing is true over here. I've got a function that comes down, then it has a sharp corner, and it goes back up again. This function has a sharp corner at 1, which means its derivative does not exist there. That means when I graph the derivative and I go over to x equals 1, there will not be any corresponding point on the graph. The key to keep track of all these ideas is to think in terms of slope. The derivative records slope. It's very easy to overgeneralize these situations. So for example, if the derivative is positive on an interval, then so is the original function. No, that's not true. If the derivative is positive, then so is the original function. So let's say I know the derivative was positive, so that means the derivative graph would have to live up here above the horizontal axis. Here's a function f whose slope is always positive, so whatever this f is, its derivative graph would live up here, as would this graph of f, which is below the x-axis. In fact, both curves are basically the same, except they're off by vertical shifts. So the derivative function for this graph and the derivative function of that graph, they're both the same, and they both live up there. So be very careful about overgeneralizing. As a word of warning, I would suggest you not use the word it. It's very tempting to say, well, it is increasing, therefore it is positive. When you say it, do you mean the function? Do you mean the derivative? What do you mean? Now we're going to look at an example function. We're going to put those ideas together. I have a function, is shown below. I'm not going to tell you the formula. The interval goes from -2 up to 6. We're going to assume that the function has intercepts at 4 and at 1 and at 6. It's kind of hard to make out, but the function appears to have a local minimum at about 5.25. We're going to eyeball it. It appears to have a flat spot or maximum at 2.5 and again a minimum or flat spot at minus 0.75. So here are some general tips for graphing the derivative. We want to graph the derivative function. Start by determining where the function has zero slope. Also, make sure to use a clean set of axes. These inputs will correspond to the x-intercepts of the derivative, because where the tangent line has a slope of 0 up here, the derivative has to cross the axis. That's going to give me minus 3/4, 2.5, and about 5.25. So I'm going to mark these with red X's or whatever, and then I'm going to draw dashed horizontal lines to divide my graph up into zones, 4 zones in this case. And then in each zone, ask yourself, is the function increasing or decreasing? Well, my function between minus 0.75 and, what did we say this was, 2.5, my function is increasing. And if the function is increasing, that means the derivative is positive. So the derivative between this point and this point, it has to live up here. Between 2.5 and 5.25, the function is decreasing. That means the derivative is always negative, which means the derivative graph is going to have to live down here. And the similar reasoning, the derivative graph is down there. So what we know is the following. We know that the derivative function, it has to cross at this point, that point, that point. The derivative graph has to live down there, and it has to live up there, and it has to live up there. Well, there's still all sorts of funky ways I could draw a curve. I could want to go like that, or something, you know, I could have things sort of wave around all over the place. Now here's where it really helps to think in terms of slope. Let's take a look at what's happening from minus 0.75 up to 2.5. The slope is always positive here. That means the derivative function is always above. The slope starts at 0. As I move in the direction of increasing x, my slopes are positive. They're getting larger, 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 larger. And then at a certain point, those slopes start getting smaller, 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 and going down to 0. So the slopes are positive and getting larger, and now they're positive and getting smaller. It seems to me, let's just take it at 1, say, that that's where the slope is largest. So that means that our derivative graph will be largest at 1. It's going to go up, and it's going to come down, and it's going to have a high point at 1. Do we know how high it goes? Well, we do if we can estimate the derivative, f prime of 1. We won't do that here, so we'll just pretend that the grid lines aren't there, and we'll just go up to, let's say, a dot right there at 1. So maybe the graph looks something like that. Whoopsie, that was supposed to come down like that. Okay, let's go over to the next zone, up to 2.5 up to 5.25. So the derivative graph is going to live below here. It's going to have to go through those 2 points. Let's take a look at what's happening over here in terms of our slope. The slope is 0. Now the slope is negative. The slope is more negative, more negative, more negative, more negative. And somewhere right around in here, the slope of that tangent line becomes less negative, less negative. So it's becoming more negative, and then it's becoming less negative, more negative to less negative. Where is it most negative? Let's eyeball it at 4. So that means the derivative graph, it's going to have to become more negative and less negative, and it appears to be most negative at about 4. So let's do something like that. Now again, we don't know how negative f prime is. If we could estimate the slope of the tangent line at 4, we would know how far down this graph goes. We won't do that here. Now, to the right of 5.25, here the slope is 0. Slope is getting larger, 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 which means the derivative has to be getting larger, larger, larger positive over there. Yeah, I forgot to account for that zone over here. So the derivative of the function was increasing in here, which means the derivative function had to live up there. Finally, let's go over to this area, to the left of minus 0.75. So that means we're looking over here. The derivative is most negative at about -2. X equals -2. And then the derivative, the slope, is negative, but it's becoming less and less and less and less and less negative until the slope hits 0. So that means that the derivative function is going to be negative, but becoming less negative. And so the derivative function might look something like that. So the final function, a very rough sketch, would be something like that. It crosses where these red x's are. It has a high point of about 1. It has a low point of about 4. Those correspond to the high points, the points on the graph where we have the most pronounced positive or most pronounced negative slopes.